Hello, and welcome to Viz-A-GoGo. I'm Hines, and we'll be starting off our tech talks today discussing fluid wall. This is a project that we started for the physical computing class here, and you see many other examples of the work made in that class. We've got the fan by Jack there that sort of tracks you as you move around, and we've got a pin, a robotic pin that draws in the back, and several other examples of work produced there. The whole idea is to sort of bring the interaction between people and computers outside of just keyboards. And so in this case, we decided to use the whole body to control sort of a fluid simulation. And I worked on this with Noreen Mahmoud there. So let's talk a little bit more about it. When I was first presented with this challenge to come up with a final project, I was thinking about things that I really liked as a child. I wanted to make some kind of playful thing. So one of the things that I really loved doing was playing with water in the bathtub. I'd have all these toys that had pumps with water, and I always going swimming. And so it seems like people like that sort of feeling of moving fluid around. There's just something about the physical properties of fluid that are engaging, at least for me. Then I also really loved light, and I used to have light shows for my family in my room. So I figured it would be a really interesting thing to try to combine the physical properties of pushing fluid around with sort of the feelings of light. And so that's sort of where the idea for fluid wall came about. It's fun to sort of shape light and have it react in the way that you might expect fluids to react. So when we're thinking about this, we need to make sure that people can manipulate water with their bodies, sort of try to make it as interactive and natural as possible, so that people already had an innate understanding of how to use this experience. And we wanted it to be playful and simple and intuitive, and we wanted it to be flexible. We didn't want a whole lot of constraints in terms of, you have to stand right here or put your body in a certain pose in order for people to recognize you. It should work just like if you were to play in a pool of water or something. So we decided in order to get this flexibility, we were going to try to use this new piece of technology that came out called the Kinect. And the Kinect is very unique in that it's not just a camera in the sense that it captures color images. It's also a depth camera. And it does this by emitting a series of infrared points. And this is sort of an image of what the scene surrounding a Kinect would look like if you took it with an infrared night vision camera. And you can see there's this guy's hand, and it's got all these little dots on it. And that's because the projector on the camera, there's this whole projector here that emits this matrix of dots. And between the projector and the sensor, there's a separation that's fixed at all points. So you can tell, the sensor can read those dots and then sort of triangulate the distance that people are from the camera. And that way you not only get sort of position vertically and horizontally, but also in depth. So that allows us to generate an image of depth that we can then feed into our software and apply all sorts of functions to it. It allows us to easily separate people from the background. And that's a big deal. I mean, movies have tried to do this for a long time by placing a big colored screen behind someone and then just erasing that color. And in modern computer vision techniques, there's also this thing where you compare two different images, and then, assuming the camera stays still, the part which is the same between the two images is the background, and you can erase that. Unfortunately, those kind of comparisons are very expensive cost-wise. And we need something that is fast to calculate. And so the Kinect gives us that speed because it just works on depth, and that depth is already created for us. And the algorithms in the Kinect program allow us to already look at different users. And so we can do things like some of the modes that you see on there, which assigns different colors to the users. Behind the hardware is a software framework called Openni. It's actually written by the people that designed the Kinect, or that worked with Microsoft to design the Kinect. And we've looked at several different other options, but Openni was the easiest to use. It has all these sort of things built into it. The body tracking, hand gestures, speech recognition, and commands, a lot of those functions are already built into the programming framework, so we don't have to write those as artists trying to get everything to work together. Then on the fluid side, we decided to use a grid-based method. There are several different methods out there right now. There's a particle method, which sort of looks at each of the particles in a fluid and they all talk to each other. And there's a grid-based method, which seemed to be the most natural method for us to use because images are also structured in computers as a grid. So we were able to take the image grid that we get out of the Kinect and directly relate it to the fluid grid that we have running our simulation. And we're using pretty much directly a system developed by Jos Stam in 2001 called the Stable Fluid Solver. And we sort of adapted his C-based code and added boundaries for cells so we could have fluid collide with people and sort of like form vortexes around, like if they hold their arm out. And also velocity. We wanted to be able to add sort of velocity elements that people sort of pushed fluid around. In order to define these sort of things, we decided to use OpenCV, which is another toolkit for programming. And it's very flexible. It's a C++ library. It's got over 2,200 different functions. And it includes, most importantly, functions for optical flow, which is a way to look at two different images and determine the differences and thus determine a velocity based on those differences. And normally that's very complicated to program, but all of it was written for us in the OpenCV library. So we're using the far-and-back method for optical flow, and it's a dense method, which means that the flow is calculated at each pixel instead of at certain regions in the screen. So it's all built in again into OpenCV. So when we were designing this, we wanted, a big concern is the behavior of the fluid, how we want it to interact. We originally intended it to be some sort of zero-G splashes thing, so when people stomp, a fluid emits from their foot and sort of just goes up and surrounds them. And we got that to work, and we felt that that was pretty fun. But then we decided on a whim to try other different ways of emitting. And we found it was really fun to have people's hands also emit fluid. So then we also showed to our class our diagnostic velocity mode, which is sort of like vectors everywhere. And it wasn't part of our original design, but people thought, hey, that looks really cool. And so we decided to incorporate that into the final piece as well. And experimenting through several other different things, we found some other modes that were pretty interesting to look at. And so that's why the final piece sort of cycles through different sort of visualizations of the fluid, as well as how people are interacting with it. And right now, there's several different areas in the screen where it has different behaviors. So at the top of the screen, nothing gets emitted. Instead, people can sort of push fluid from side to side. And towards the bottom of the screen and in the middle, you do have emission defined from the hands. We think that's probably another way that we could further refine this project, is sort of adding more regions or features between the different parts of the image. So that brings us to the future work. Right now the resolution is really small compared to what it could be. The Kinect can give us a maximum of 640 by 480 resolution, But right now it's running at 128 by 128 because that's as fast as our poor little computer can process the complicated fluid simulation. So some ideas to make the fluid simulation faster might be to optimize the algorithm to use multi-threading features on processors. We have a quad-core processor, which means that theoretically could run 4 threads at the same time, but we're only using one right now. Additionally, there's been experiments using fluid simulation on graphics processors, and those processors are specially designed to handle the types of equations that we typically see in these situations. They're usually used for like display for games, but NVIDIA's developed this CUDA framework that allows you to program other applications on those processors, and it is fast. I've looked at some of the demos and it's like incredible. They can achieve like full screen resolution fluid simulations. So that's something that we're thinking about doing. And also the multi-user mode right now doesn't quite work. It can detect the different users, but the colors are not moving properly between the different users. So that's something we would like to work on in the future. But that is what we have right now. Are there any questions? If not, then you're welcome to go and experiment with the wall and sort of have fun with it. Don't be afraid, get up close to it. That's all I have. Thank you for your attention.